Okay, welcome everybody. Today we are looking at the substance identity or specific heat lab. This is the equation that we are going to be and have been dealing with for a while now. Heat equals mass times specific heat times change in temperature. This is what we are looking at today. Okay, we're looking at the C. Now, to help you along, specific heat is actually specific heat capacity. Okay, and that's where they get the C from. So just looking at procedure of this lab, okay, pretty straightforward. Hot water bath, we'll show you how to make that. And actually there's a picture of a hot water bath right here. Okay, so we're going to be making a hot water bath, heating that to a boil. There's going to be 20 grams of copper shot, just copper pellets in a test tube. And we're going to have 20 grams of aluminum. Same deal. We're going to put those in the hot water bath, again, just as pictured. We're going to have water then sitting in another cup, okay, cold water just from the faucet. It'll be sitting in another cup. We are going to be taking the initial temperature and final temperature of that water. We're going to be dumping the hot metal into it because as the metal is heated in this hot water bath, the temperature of that metal is going to go up. We're going to pour that metal into the beaker, as you see here in this picture, and we're going to see what the temperature does. We can hypothesize that if that is cold water and we're putting hot metal into it, the water is going to increase. The difference in this lab is that we have two substances. We have copper and we have aluminum. We want to see if we use the same amount of different substances, will it affect the water differently? One could make an assumption that, hey, if I have 20 grams of something and I'm putting it into water and both of them are going to be at the same temperature, it should raise the water by the same temperature. That would be one hypothesis. Okay, we can see if that is true or untrue. I've made a data table. Okay, I have substance, mass, initial temperature of water, final temperature of water. We can fill a couple of these things in now, and we'll come back to the rest of them later. So we have mass of the copper is going to be pre-measured 20 grams, mass of aluminum pre-measured 20 grams, and the rest of this we can come back and fill in later. Okay, welcome to the specific heat lab. Let's walk through our materials and our setup and see what we have. First off, we have hot water boiling. Okay, we have a probe set up. We'll get into that more later. We have two graduated cylinders, okay, to measure volume accurately. We have one beaker with just cold tap water in it. We have two beakers set up over here, simply styrofoam cups sitting inside a beaker so they don't fall over. And inside those we have temperature probes. And then over here we have two containers. Okay, one has copper, one has aluminum. They are labeled. They have both been measured out with 20 grams each. And then in the back we have two test tubes waiting for them. So that is our setup. I've transferred the copper and the aluminum into their corresponding test tubes. The copper is, for lack of a better term, copper or orange or bronze in color. The aluminum is gray or silver in color. Now I'm going to transfer those to the hot water bath. So that's 20 grams pre-measured. Both are fully submerged. All of the metal, shake this one down a little bit. There we go. I want to make sure all the metal is underneath the surface of the water, which it is. I'm going to let that cook now for approximately 5 minutes. In 200 milliliter graduated cylinders, I measured out 40 milliliters each of water. Okay, room temperature, just tap water. I guess I shouldn't say room temperature is just tap water, so a little bit under room temperature. I'm going to take those, I'm going to pour them directly into the styrofoam cups that are sitting there. And now they're ready for the metal. Just to verify, I've had both copper and the aluminum sitting in the hot water bath. The temperature of the hot water bath is 100.1, 100 degrees, right around 100, right around boiling, which is perfect. I've let them cook for 5 minutes. I now can make the assumption that the temperature of the metal is the same temperature of the water. So since the water is 100 degrees, the metal, since it's in the water, in that same system, the metal is also 100 degrees. Now that I have everything set, I have both probes into their corresponding styrofoam cups. They're both sitting right almost exactly at the same temperature at 20.6 and 20.5 respectively. The red probe number 1 is going to be copper, and the blue probe number 2 is going to be aluminum. Now I'm going to try to simultaneously add the copper and the aluminum to their cups. Now I will start the chart and add the metals. I can see now that the temperatures are decreasing, so the metals have added all of their heat or energy to the water. Now we can check our data. There's our graph scaled properly. We can see a sharp increase in temperatures. One line is higher than the other line. That's what we need to examine. And then we start to see a decrease as they start to technically heat the environment, which would be the classroom, and their temperatures start to drop. As we look at our data, we see that they start at 20 degrees. We have temperature 1, temperature 2, and time here. And as that time increases, we'll see them increase from 20.45. They spike very quickly. I'm seeing 27 degrees on temperature 2. I'm seeing 25.7 on temperature 1. And then I start to see a decrease. I see 27 starts dropping to 26.9. And as I scroll down, I see 25.7, and then I see 25.6. So both of them start to decrease at that point. Let's go through the first question together on page 8 here. It says, calculate the heat absorbed by the water, okay, when the copper was dumped into it. Okay, so we want to know about water here. So, first off, this is what we're solving for. So, as always, we'll make that our x. This is what we want. We want heat. Heat is Q. Okay, and it wants to know about water. Water is really important. Water is something you need to know. Its specific heat is 1 calorie per gram degrees Celsius. That is something you just need to know. So I can go ahead and plug that in right here. The other information I need is its mass. Well, I used 40 grams of water because if I zoom way out here, if I use 40 milliliters of water, milliliters and grams of water, 1 milliliter equals 1 gram. So they're equal. So that's how I get 40 grams of water. I look at my information. Now I need to know my TF and my TI of water. Well, I can look back to my data table here. And if I'm talking copper, well, here's my initial temperature. Okay, so I'm going to get 20.5 for my initial degrees Celsius. And then my final for copper, 25.7. Okay. So I have all my information. I now plug it into my equation right here. So I'm solving for Q. I can make a Q, I guess, I don't know, just leave it X, make it Q, I don't really care. I'm looking at 40 grams, 1 calorie per gram degree Celsius. T final is 25.7 minus T initial of, what was it, 20.5. Okay, now I flip over to math mode. Simply do what's in the parentheses first. 25.7 minus 20.5 gives me 5.2. So then 40 times 1 times 5.2. That solves for my Q. 40 times 1 times 5.2 gives me 208 calories. That is how much water. That's how much water was, or I'm sorry, how much energy was absorbed by the water when the copper was dumped into it. Well, now this wants to know about the aluminum, and then it asks, are they the same? Why or why not? Okay, so we're looking at our graphs here. If we have our graphs, we do want to go through and make sure we know this was our aluminum line, and this was our copper line. Okay, so aluminum made the water have a much higher temperature, okay, and we kept our data over here. The high temperature for, again, this is copper here, this is aluminum here. Aluminum got all the way up to 27, copper only got to 25.7. So then we're going to see what that means. It asks about, okay, how much heat did aluminum give to that water? And then we have to talk about, okay, if they are the same, why? If they're not the same, why? So that should be a pretty good start for you. Here's your data table. Now you can walk through the rest of it.